A Brief History of Time by Stephen Hawking. Read by Mr. Narrator. Chapter 2, Space and Time. Part 1. Our present ideas about the motion of bodies date back to Galileo and Newton. Before them, people believed Aristotle, who said that the natural state of a body was to be at rest and that it moved only if driven by a force or impulse. It followed that a heavy body should fall faster than a light one because it would have a greater pull towards the earth. The Aristotelian tradition also held that one could work out all the laws that governed the universe by pure thought. It was not necessary to check by observations, so no one until Galileo bothered to see whether bodies of different weight did in fact fall at different speeds. It is said that Galileo demonstrated that Aristotle's belief was false by dropping weights from the Leaning Tower of Pisa. The story is almost certainly untrue, but Galileo did do something equivalent. He rolled balls of different weights down a smooth slope. The situation was similar to that of heavy bodies falling vertically, but it is easier to observe because the speeds are smaller. Galileo's measurements indicated that each body increased its speed at the same rate, no matter what its weight. For example, if you let go of a ball on a slope that drops by 1 meter for every 10 meters you go along, the ball will be traveling down the slope at speeds of about 1 meter per second after 1 second, 2 meters per second after 2 seconds, and so on. However heavy the ball, of course, a lead weight would fall faster than a feather, but that is only because the feather is slowed down by the air resistance. If one drops two bodies that don't have much air resistance, such as two lead weights, they fall at the same rate. On the moon, where there is no air to slow things down, astronaut David R. Scott performed the feather and lead weight experiment and found that indeed they did not hit the ground at different times. They hit the ground in the same time. Galileo's measurements were used by Newton as the basis of laws of motion. In Galileo's experiments, as a body rolled down the slope, it was always acted on by the same force, its weight, and the effect was to make it constantly speed up. This showed that the real effect of force is always to change the speed of a body rather than just to set it moving, as was previously thought. It also meant that whenever a body is not acted on by any force, it will keep moving on in a straight line at the same speed. This idea was first stated explicitly in Newton's first law of gravitation in his book Principia Mathematica, published in 1687, and is known as Newton's first law. What happens to a body when a force does not act on it is given by Newton's second law. It states that the body will accelerate or change its speed at a rate that is proportional to the force. For example, the acceleration is twice as great if the force is twice as great. The acceleration is also smaller the greater the mass or quantity of matter of the body. The same force acting on the body of twice the mass will produce half the acceleration. A familiar example is provided by a car. The more powerful the engine, the greater the acceleration, but the heavier the car, the smaller the acceleration for the same engine. In addition to his laws of motion, Newton discovered a law to describe the force of gravity, which states that every body attracts body with a force that is proportional to the mass of each body. Thus, the force between two bodies would be twice as strong if one of the bodies, say body A, had its mass doubled. This is what you might have expected, because one could think of the new body A as being made of two bodies with original mass. Each body would attract body B with the original mass, and the other had 3 times the mass. Then the force would be 6 times as strong. One can now see that while all bodies fall at the same rate, a body of twice the weight will have twice the force of gravity pulling it down, but it will also have twice the mass. According to Newton's second law, these two effects will exactly cancel each other, so the acceleration will be the same in all cases. Newton's law of gravity also tells us that the farther apart the bodies, the smaller the force. Newton's law of gravity says that the gravitational attraction of a star is exactly 1/4 that of a similar star at half the distance. This law predicts the orbit of Earth, the Moon, and the planets with great accuracy. If the law were that gravitational attraction of a star went down faster or increased more rapidly with distance, the orbits of planets would not be elliptical. They would either be spiraled into the sun or escape the sun. The big difference between the idea of Aristotle and those of Galileo and Newton is that Aristotle believed in a preferred state of rest which anybody would take up if it were not driven by some force or impulse. In particular, he thought that the earth was at rest, but it follows from Newton's law that there is no unique standard of rest. One could equally well say that body A was at rest and body B was moving at constant speeds with respect to body A, or that to body B was at the rest and body A was moving. For example, if one sets aside for a moment the rotation of the earth and its orbit round the sun, one could say that the earth was at rest and that a train on it was traveling north at 90 miles per hour, or that the train was at rest and the earth was moving south at 90 miles per hour. If one carried out experiments with moving bodies on the train, all Newton's laws would still hold. For instance, playing ping pong on the train, one would find that the ball obeyed Newton's laws just like a ball on a table by the track. So there is no way to tell whether it is the train or the earth that is moving. The lack of absolute standard of rest meant that one could not determine whether two events that took place at different times occurred in same positions in space. For example, suppose our ping pong ball on the train bounces straight up and down, hitting the table twice on the same spot 1 second apart. To someone on the track, the two bounces would seem to take place about 40 meters apart, because the train would have traveled that far down the track between the bounces. The non-existence of absolute rest therefore meant that one could not give an event an absolute position in space, as Aristotle had believed. The positions of events and the distance between them would be different for a person on train and on the track, and there would be no reason to prefer one's position to the others. Newton was very worried by this lack of absolute position, or absolute space, as it was called, because it did not accord with his idea of absolute God. In fact, he refused to accept lack of absolute space, even though it was implied by his laws. He was severely criticized for his irrational belief by many people, most notably by Bishop Berkeley, a philosopher who believed that all material objects in space and time are an illusion. When the famous Dr. Johnson was told of Berkeley's opinion, he cried, "I refute it thus," and stubbed his toe on a large stone. Both Aristotle and Newton believed in absolute time. That is, the belief that one could unambiguously measure the interval of time between two events, and that this time would be the same whoever measured it, provided by a good clock. Time was completely separate from and independent of space. This is what most people would take to be common sense view. Time was completely separate. However, we have had to change our ideas about space and time, although our apparently common sense notions work well then dealing with things like apples or planets that travel comparatively slowly. They don't work at all for things moving at or near the speed of light. The fact that light travels at a finite but very high speed was first discovered in 1676 by Danish astronomer Ole Christian Romer. He observed that the times at which the moons of Jupiter appeared to pass behind the Jupiter were not evenly spaced as one would expect if the moons went around Jupiter at a constant rate. As the Earth and Jupiter orbited around the Sun, the distance between them varies. Roman noticed that ellipses of Jupiter's moon appeared later the farther we were from Jupiter. He argued that this was because the light from the distance of Earth to Jupiter were, however, not very accurate, and so his value of speed of light was just 140,000 miles per second compared to the modern value of 186,000 miles per second. Nevertheless, Royer's achievement in not only providing the light's travel at a finite speed but also in measuring that speed was remarkable. Coming it did 11 years before Newton's publication of Principia Mathematica. A proper theory of propagation of light did not come until 1865, but the British physicist James Clerk Maxwell suggested in unifying the partial theories that up to then had been used to describe the forces of electricity and magnetism. Maxwell's equation predicted that there could be a wave-like disturbance in the combined electromagnetic field and that this would travel at fixed speeds like ripples on a pond. If the wavelength of these waves, the distance between one wave's crest and the next, is a meter or more, they are what we now call radio waves. Shorter wavelengths are known as microwaves, a few centimeters, or infrared, more than a 10,000th of a centimeter. Visible light has a wavelength of between only 40 and 80 millionth of a centimeter. Even shorter wavelengths are known as ultraviolet X-rays and gamma rays. Maxwell's theory predicted that radio or light waves should travel at a certain fixed speed, but Newton's theory had got rid of the idea, absolute rest. So, if light was supposed to travel at a fixed speed, no one would have to say that fixed speed was to be measured relative to